This is part 2 of the nuclear chemistry notes. If you are just joining us, go back and watch part 1 before jumping in here so that you are all up to speed. So we just finished talking about alpha, beta, and gamma decay. So right now we're just going to kind of recap what those are and then look at their actual reactions. So alpha decay, we said, is when we have a large nucleus that sheds 2 protons and 2 neutrons because it's unstable, it's too big, so it sheds this large particle to just quickly become more stable. 2 protons, 2 neutrons, and that is just a helium nucleus made of mass 4, protons 2. So you could write the helium symbol such as this. You could also write it like this with an alpha interchangeably with that helium. Either one is fine. So if you have a reaction written like this, where you've got a really unstable radioisotope, that would be polonium-209 in this case, and so it says, all right, I'm going to spit out 2 protons, 2 electrons, there's my alpha particle, what do I make after that? We're going to use the law of conservation of mass to help us solve for our unknown blanks over here. So think of the arrow as an equal sign, and we would say 209 equals 4 plus what? This is going to be 205. Double check yourself. 205 plus 4 is 209. Correct. So our mystery element over here has a mass of 205. That should make sense because our original shed 4 giving us 205. Now for the bottom, we have 84 protons to start with. We're going to get rid of 2, meaning we have 82 left at the end. Again, check your math. 82 plus 2 is 84. Arrow is the equal sign for math. Then to find your element symbol, look on the periodic table for atomic number 82, and you will find lead. So our mystery element that was produced in this nuclear reaction is lead-205. Next we have beta decay, and again in part 1, if you were tracking along with us, we said beta decay is when a neutron becomes a proton. And this happens by releasing a negative charge. Again, think about this, neutron has no charge. If it releases negative charge, now overall it's positive, making it a proton. Because our neutron is becoming a proton and releasing an electron, there is no change in the mass. Just a little note to remember, no change in the mass. Here's our beta symbol, releasing an electron, and it has no mass. And then remember we talked about it's kind of funky that it has a -1 atomic number, but that is what we have agreed upon in the chemistry community. For beta particle, it has -1 atomic number. So again, same process, our mass is not going to change, so there's 222, and then our neutron becomes a proton. So think about it, we're going to gain a proton in our final product, so this should be not 86, but 87 as we gain 1. The math should also make sense here, but I often see students see the -1 on this guy and think, oh, I need to subtract 1, it's going to be 85. But that's not the case even mathematically. If you make this an equal sign to cancel this out, you would add 1 to both sides, making it 87. So mathematically, check yourself, adding a proton is beta decay. This is francium. If you look it up on the periodic table, that will tell you the element symbol. In case you were wondering where I got francium from, look up the atomic number and you'll find the element symbol. Lastly, gamma decay is radiation that's emitted in the form of a really high energy wave. It's not an actual particle. It's just, I say just, but it's a very strong and dangerous form of radiation. Because it is energy and it's not actually a particle, so it can pass through essentially anything and cause danger. It can even burn you without even knowing it's in the air. Okay, so its radiation is emitted in the form of a dangerous high energy wave. So if you were writing a reaction for this, nothing changes, which is another reason why it's so dangerous, because it's kind of a blind radiation. You don't even know it's there until it's affected you. No mass, no particle of the protons changing. Before we look at other reaction types, we're going to take a second on page 5 and 6 to just look at what we've got. Both of them are similar. One's with alpha decay and the other is with beta decay. For each reaction, you'll use a periodic table. You'll find the isotope name, the number of protons and neutrons in the nucleus, and then the corresponding nuclear symbols. So this is really just like review from last week, but now within a reaction. And then 2 and 3 are like the example on the front. You will use the law of conservation of mass to fill in the blanks that are provided. And that's the same for both alpha and beta. So use a periodic table to go through these, and then come back with me here to fission and fusion. Fission and fusion are the last two types of nuclear reactions, and fission is used actually in power plants to get nuclear energy. And the way that this works is they take an unstable atom or radioisotope, and so it's going to be a really large atom, and they hit it with a neutron. And what happens is lots of energy is released, and our big atom is split into two smaller. So this is the division. Fission is division of a large nucleus into smaller ones. And what happens in a nuclear power plant is that this reaction releases a lot of energy, which heats up this water bath that it's in, and that causes steam, which then goes into the turbines, and then it can convert that energy into usable sources like electricity and other forms of energy that we use. So that's fission. Fusion, on the other hand, is the joining of atoms. And it looks like this if I were to draw a picture. So let's say joining of nuclei. And fusion only happens on the stars and in the sun. It releases so much energy, more than fission. And it is not a reaction that we have actually been able to figure out how to do on Earth, which is probably a good thing, because it's so much energy. There would be if there was an accident, there would be lots of repercussions and death and other things. Even fission, which releases energy, but not as much as fusion, has caused its fair share of accidents. If you think about some different events in history from nuclear power plants, you may already even be familiar with them. We will be doing a little web quest on Tuesday, researching a few different accidents that have occurred. So that is one drawback of nuclear energy. Although it can be very useful, you have to be very, very careful. If there is an accident, then it can cause explosions, death, radiation, which can be around for years and years depending on the half-life of the radioisotope, and that can just lead to lots more problems. So there can be dangers with nuclear chemistry, nuclear reactions, but there are so many positive things if we can use them responsibly and know what we're dealing with, then it can be really helpful. So that is the gist on nuclear chemistry, reactions of the nucleus with protons and neutrons trying to become stable. We've got alpha, beta, and gamma decay, and then fission and fusion.